Okay, hi everyone. So let's start with looking at number 2. So what is going on here? So I need to give you some context. So what we have, anytime you have a linear map from a vector space to another, you should immediately think about a few things. First of all, you definitely have the null space of T as a subspace of the domain, and you always have the range of T as a subspace of the target space. Okay? And you also know from rank nullity that the dimension of V, or the fundamental theorem of linear maps, also called rank nullity, is equal to the dimension of the null space of T plus the dimension of the range. So that's one of those fundamental theorems that relates the dimensions of these subspaces in completely different spaces. Now, what you also know is that if V is an inner product space, then you have a notion of orthogonality, and you can look at the null space of T perp. So all the vectors that are orthogonal 90 degrees to the things in null T. Okay. And then from a direct sum decomposition of V, you know that the dimension of the full space is equal to the dimension of each piece added up. So this gives us a very similar looking formula from which we conclude that, well, these are both the same, so these numbers have to be the same. So the range of T and the null space perp have the exact same dimension. Wouldn't it be nice if T was invertible between these spaces? And in fact, it always is. Okay, I mean, T might not be invertible. T might have a big null space, lots of vectors get mapped to 0, failing injectivity, and hence not invertible. But now you have, from a combination of the direct sum, the orthogonal direct sum decomposition of V, and the rank nullity fundamental theorem, you know that these two spaces are the same dimension. So you remember that if we restrict, so certainly we can restrict T to the null space of T perp. Okay, that just means, this is just the map T, but now we're going to only feed it vectors in here. Okay, so these are just equal. Also, once you map something over, it's in the range of T. So the range of T and the range of this are the same. And so actually what we're going to see is that this thing is invertible. So first of all, this thing is a map from null T perp to the range of T. And so it's a map between two spaces that have the exact same dimension. That means that to prove that it's invertible, that the inverse exists, all we have to do is prove it's injective. Okay? Remember, a linear map is injective when it has no null space. But hold on a second. This T restricted to thing is just T. It's just T when we're plugging in these vectors. And what are we doing? We're plugging in, now we're only plugging in vectors that are orthogonal to the null space, right? But this direct sum decomposition means, that the vectors in the null space intersect the null space of T perp. It is nothing. It's just the 0 vector is in there. And that means that T restricted to the null of T perp only has the 0 vector in its null space, which means this is injective. And since it's an injective map between two spaces of the same dimension, it is invertible. And hence we have proved our first theorem that T restricted to the null of T perp is invertible. Inverse. So this thing, inverse, exists. The inverse map. The inverse map is it. What is it? What does the inverse map do? It sends the range of T back to the null of T perp. Okay? It just undoes what T did when it took vectors from here to here. Now we're undoing it. That's what the inverse does. Okay. So that's not actually that bad to prove that this is a bijective map. The key was knowing that the range and this null t perp have the exact same dimension. That was key. And then we just need to check that this is bijective, but like we're only feeding it, it can't have a null space because we're feeding it things that are orthogonal to the null space. So this is injective and hence it's bijective. Okay. All right. So the pseudo-inverse. Well, the pseudo-inverse is definitely going to use the inverse that we just talked about, but it's going to be a little different. So the pseudo-inverse, maybe I'll write it like this. Okay, I don't know. Oh, that's how I'll write dagger. I'm not sure how to write that. What's it going to be defined to be? Well, it's definitely going to use the inverse of t when restricted to the null t perp. But first, it's going to do the orthogonal projection onto the range of t. In other words, remember, t goes from capital V to capital W, and t dagger is going to go from capital W to V. So it's going to sort of undo, it's not going to invert t because t might not be invertible at all, but it will be the best. It's a pseudo inverse, okay? And so it's definitely going to go the other way, okay? So what do? We take a little vector w, and remember, we know that w is the range of t, direct sum, orthogonal direct sum, the range of t perp. Right, so a little w can always be written as something in the range plus something in the range perp. And first what we do when this hits it just throws away that piece and takes w1. And then it inverts it from that range back to v, and it spits it out inside of the null t perp, inside of capital V, or capital V. Yeah. Okay, so in other words, this is the definition of pseudo-inverse. Okay. It inverts t where it's possible to invert it. Okay. But in order to do that, it first has to project it down onto that space, the range, which has the same dimension as the null of t perp. Okay. So that's what it does. Now, what do we have to prove about this? Let's prove. Now, take a moment, maybe try even this proof yourself, although it's a little confusing. You're going to see it's not hard, but at least read this yourself. Pause the video and do that. Okay, so how do we prove this? Let's look at this first one. So remember, t dagger sends us from capital W to V, and then t sends us from V to W. So t after t dagger sends us from W to W. Okay. Now, what is the projection onto the range? That also goes from W to W, and it takes a little vector and just projects it onto the range of t, which is a subspace of W. Okay. So let's see if these two things do so if we take some vector little w in big W, then little w has a decomposition coming from range of t, orthogonal direct sum, range of t perp. That is all of w. And so here, let's put this as the part in the range, and this is the part of w in the perp space. What does the projection do? It just, projection range t of w is just that part. It just throws this part away, and it spits out this part. So now we just check if the other side does the same thing. Okay, so now t dagger hits w, and what's the definition of t dagger? And then we're going to do t. So t dagger does the t inverse on null of t perp, inverts it where it's possible after projecting onto the range of t, and it does that to w. So to project w on the range, we do the same thing as projection on the range. We spit out w on the range, and now this piece is the identity, because t and t inverse give you the identity. In other words, you know, t is equal to t restricted to the null of t perp when you feed them things in the null of t perp. And so, you know, I guess what I'm trying to say is that this is a bijective map, and so it's just defined by undoing what t does on the range, and so that's why it's equal to the identity on this, and so we get the same thing. Okay, let's look at the other way. Why now? What's the next thing we have to do? We have to show that t dagger t is equal to the projection onto, I believe, the null of t perp. So remember the definition of t dagger. It inverts t on the null of t perp, and then it projects onto the, well, actually it first projects onto the range, and then it inverts that from the range back to null of t perp. Okay. And then we're supposed to do t first and then t dagger, so we do t first and then t dagger. And the question is this equal to the projection here? Okay. Well, let's take an element of v and let's feed it to both sides. An element of v can be written as something in the null space plus something in the null space perp. Okay? And when t eats that thing, it, you know, tv is tv in null space plus t in v perp, and this is 0 because vn is in the null space. Okay? And then so that's what t does to it. Now we have to do projection onto the range, but this is already in the range, so the projection onto the range just gives us the exact same thing, which is the vector tv perp, which is in the range. That's why this didn't do anything. And then this just inverts it, and that means that we get the identity, and so this is v perp. So this whole thing on the left ate a v and gave you v perp. But that is exactly what the projection onto the null space of t perp does. Okay, so we're good there too. Now, if t is invertible, then the pseudo-inverse is actually the inverse. And that's pretty clear because you invert t on the null of t perp. But if t is invertible, then when we take v and we do null of t o plus null of t perp, this piece is just 0, meaning that v is this whole thing, and so t restricted to that thing is just t, and so we don't, projecting onto the range of t, the range, this is invertible, so the range of t is the entire space w. So projection doesn't do anything, and then this doesn't do anything, and so we just get t inverse. Now, what is this part? Okay, so you should read number 5. Pause the video and just read this part here, at least. In other words, say we have some data vector b over here in our big space capital W, and we're trying to get to it by tx equals b. Now, even if there's no solution, in other words, if the range is down here and b is outside of the range, that means that there's no solution. There is no tx that equals b. But even in that case, of all the tx's, that one, that one, that one, that one, all these tx's in the range, which one is the best? Well, the claim is it's this one. Now, why? Well, we just proved that t after t dagger is the projection onto the range. So this thing just orthogonally projects onto the range. That means we got 90-degree angle there. Okay? And with that, another way of saying that is that if you do b minus this thing, or this thing minus b, that's 90 degrees to the range. okay? But that means if you take any other tx and you do their dot product, you get 0. Okay, in other words, what we have here, let me try to get rid of all this junk. This formula right here, which follows because this is just the projection onto the, this just projects B onto the range. This formula right here means that if we take any other tx, like that one, and we form this right triangle, it's a right triangle. Okay, if we form this triangle, it is a 90-degree triangle. But that means we have Pythagoras. Pythagoras says that the length of this green side, which is down here, is bigger than, the hypotenuse is longer than any of these two sides, including this one. In other words, of all the tx's in the range, the one that makes the smallest error is this one right here, t after t perp. And so if we're trying to solve tx equals b, we should take x to be t dagger b. Okay, and then if you plug this in for x, we get t times t dagger b, and that's exactly the shortest possible, the shortest distance of all the distances to things in the range. Okay, good. What about this one? Okay, so if x is in this space, this is a vector plus something in the null space, so I'm just going to write that vector plus something in the null space, little n is in the null space of t. So if x looks like this, then first of all, remember that t dagger b is in the null of t perp, because remember the definition of t dagger, it was defined to be inverting from the null of t perp. In other words, it spits out things in the null of t perp after projection onto the range. So whatever t dagger does, it eats some stuff. So if it eats b, it projects it onto the range, and then it inverts it and throws it back into the null of t perp. Okay, but that means that this thing and this thing are orthogonal. They form a 90-degree triangle with each other. So that's this 90-degree triangle here with the n and this, and their sum is x. And so guess what? X is the hypotenuse, and that is bigger than this side, t dagger b. And that's exactly what we were trying to prove. This is the hypotenuse, which is bigger than one of the sides of a right triangle. We threw away the other side, which is how we got an inequality. Okay, the Pythagoras theorem actually says that the sum of the squares is equal, but if you throw away one of the sides, then you just get that the hypotenuse is bigger than a side. Okay. So the pseudo-inverse, for us, we've seen, I've talked about how the pseudo-inverse can solve these problems for you and spit out the right function that fits your data. But there's even more ways to use it, so I'll just briefly mention it. Let's say you're trying to solve some equations. What you can do is you take a guess. So here's my first guess. This is called Newton's method. And you just guess anywhere. And then what you do is iteratively you use the derivative, and you step there, 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 and each step you get closer to a solution. So in other words, this blue curve with these two pieces is the set of solutions to an equation, actually a nonlinear equation, f of xy equals 0, where f is some nonlinear function. Okay, I think this particular blue curve, we need like an x to the 4th plus like 3x to the 3rd y plus blah 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 equals 0. And so there's infinitely many solutions. All these points on the curve are a solution to our nonlinear equation, one equation in two variables. And so what you do here is you use calculus, and you say, look, and instead of x comma y, let's just say capital X, where capital X is just a shorter way to say that. Now, what we're going to do here is we're going to start at a point P, where P might be like, like x naught, y naught, some point P, okay? And what we have is we want to find a movement vector h. A movement vector h like that. That'll be our h. Such that f of p plus h is 0. Okay? So we want to find how we can, f of p, if we just choose p randomly, we're just going to guess p, f of p is probably not going to be 0. In other words, p, we're not just going to guess a solution, unless we're super lucky, but probably f of p is not 0. Okay, so then how do we move to make it 0? Well, we know that this is basically equal to, it's basically equal to f of p, which is not 0. If it were 0, we'd be done, but this is probably not 0. Plus what? The derivative of f. The derivative of f applied to the movement vector h. You could even call this grad f or whatever you want, but it's in general it'll be a Jacobian matrix. It'll be a linear map. In other words, the derivative is a linear map. In a matrix, you'd call it the Jacobian matrix. And what does it do? It multiplies a movement vector and gives you an output vector. And that output vector, in this case, is one-dimensional, but in other cases, it would be higher dimensional. And then we add that to f of p, and we try to get 0. Okay. So what should we do? How do we find h? Well, we should, so this we want to be 0. So what we should do is we should solve df, this is a matrix, or a linear map. In other words, this is our t. H equals minus f of p. Okay, this is our vector, or it's our non-zero number. Tx equals b. Now, in general, there will not always be a solution that exactly produces minus f of p. So what we do is we set h to be the pseudo-inverse of our Jacobian matrix applied to negative f of p. Okay, and that's how you find the movement vector. That's how I computed these updates. This update. You just keep doing this. You repeat this each time. You should evaluate the Jacobian at p each time. So this is the Jacobian evaluated at p, and then this is the Jacobian evaluated at p pseudo-inverse. So anyway, this allows you so the pseudo-inverse, in other words, allows you to solve non-linear systems of equations approximately by just solving linear systems a bunch of times, getting closer and closer to a solution. And those linear systems actually will not have solutions, typically, and so that's why we use the pseudo-inverse. Because it's just going to work. So this is how you do Newton's method in higher dimensions for nonlinear equations. So, pseudo-inverse, it's a good one.